Mhlongo nobubi. Msindo bafana.
Music covers.
Ngiyasenda la ku-Google Mind. Lecture siqalile. Okade ngikhuluma naye ngomuntu. Each of the other class is 26 people, but only 6 people come. The rest they are on holiday. All right. Good day, guys. How are you? Let's share the screen. Right, where we want to share the screen. Share document. Right, just go. Right, so last time we were here, we talked about the coulomb, the current, and we did these two questions and we solved them, and then people were tired. So today we're starting on what? Measuring potential difference, voltage and current, right? So what is a potential difference in the beginning? A potential difference across an electrical component is needed to make an electric current flow in it, right? A potential difference is like EMF. Remember last week we talked about EMF. So a potential difference across an electrical component is needed to make an electric current flow in it, right? Cells or batteries often provide potential difference needed. These are examples of what? Potential difference. So potential difference PD, which is called voltage, it may be confused with electromotive force. There, what I was saying. Note that this is not really a force. It is measured in volts, not newtons. So EMF is some sort of potential difference, but they are not the same. Do not confuse them, right? They are not what? The same. So potential difference is often called the voltage and is measured in what? Volts, right? Measuring potential difference. For example, we say potential difference is measured in volts, of which on our calculations and our formulas, we're going to refer to it as V, right? So the potential difference across a component in a circuit, the potential difference across a component in a circuit is measured using a voltmeter. So remember last week when we said we put a battery, etc., and then a light bulb lights. A circuit is a full complete cycle, a full connection of a potential force or electromotive force together with a light bulb or resistor whatsoever, a load, with no open circuit, the full round circle, that's a circuit. So a potential difference across a component in a circuit is measured using a voltage, right? So the voltmeter must be connected in parallel with the component. Look at this. Let's say, for example, this is your light bulb, right? Your light bulb. Or whatever load it is, your electric kettle, your stove, or whatsoever. So if you want to know what potential voltage, what potential difference, what voltage it's utilizing, you connect across it, not parallel to it, across it. So which means it's a line, right? An electrical wire going like this. That electrical wire, that electrical wire is your load there going like this. So the wire goes in and the wire comes out on the neutral there. So your potential difference, you come and plug one leg here, one other leg. Across must be parallel to your device. So here is your voltmeter represented by V. Here is your device, a light bulb or load. See, it's in parallel, connected across it. So the voltmeter must be connected in parallel with what? With the component. Now, measuring current. Current is measured in amperes. We discussed that last week, and we represented it with A, a big capital letter A. So the current flowing through a component in a circuit is measured using a what? An ammeter. So take note, the other one we're using a voltmeter. Now we're utilizing what? An ammeter. The ammeter must be connected in series with the component. So if you check what we were talking about last time was a voltmeter, we said it's connected across, right? Said it's connected across. But for an ammeter, it's connected in series with the component, right? So now, here we go. What they are saying here is this. Let's get it. That's what they're talking about. Let's say this is your component here, represented by an X, right? Instead of connecting across, you connect your ammeter in series, like this. Right, you see, in series, thereby you're measuring current. But last time when we're talking, we said the voltmeter, we put it across. This would be a voltmeter. You see, the voltmeter is in parallel, but your ammeter is in what? Is in series with your component. All right. Now, there's what is called the resistance. Let's check. Yeah, any comments from people? I'm hearing cool. No way. So there's what is called the resistance. What is the resistance? There is a resistance to the flow of an electric current through most conductors. There is a resistance to the flow of an electric current through most conductors. That is through a conductor, or for example, let's say when you're driving a car, no matter how much you speed or whatsoever, when you speed, there's always that wind which is pushing you back, which is hitting on the car, right? That's a resistance. So in electricity, it's the same. So there's a resistance which is trying to stop those electrons from flowing and then from giving us an electric current. So there's a resistance to the flow of an electric current through most conductors. The resistance in a wire increases. You must take note of this one. This is serious. It leads to Ohm's law. Right. The resistance in a wire increases as 1, the length of the wire increases. 2, the thickness of the wire decreases. Right. So the smaller the wire and the shorter the wire, the less resistant it is. But the longer the wire and the thicker the wire it is, that's the problem. The higher the resistance is. Now, the resistance of a long wire is greater than the resistance of a short wire because electrons collide more with more ions as they pass through. That's what I was saying earlier. But take note of these reasons so that when on the test we're asking you why, you have the reason why. You don't just say a longer wire has more resistance than a shorter wire. Why does it have a longer resistance? It's because on a longer wire, there are more collisions with more ions as they pass as compared to a shorter wire. So the relationship between resistance and the wire is proportional, right? The resistance between the wire and its length is proportional. So in other words, resistance is directly proportional to length, right? For example, take this one. There's a potential difference of 1.5 volts in the circuit, and then there are 2 components. Hence, there's going to be high resistance, right? There's 2 things here, high resistance, low current. Same potential difference there, 1 load, 1 light bulb, which means less resistance. So low resistance, high current, high resistance, low current. So if there's more loads, there's gonna be more resistance. So if there's more resistance, we're gonna have less current. This one is gonna chow, and this one is gonna chow. If, however, there is 1 load, that means there is less resistance. Less resistance means what? A high current, as suggested there by the diagram. Now, the resistance of a thin wire is greater than the resistance of a thick wire because a thin wire has fewer electrons to carry the current. Listen to this one. The resistance of a thin wire is greater than the resistance of a thick wire. Why? Because a thin wire has few electrons to carry the current. The relationship between the resistance and the area of the cross-section of the wire is inversely proportional. This is what they are trying to say mathematically. R is inversely proportional to cross-sectional area. So now we talked about length before. In other words, they are saying resistance is directly proportional to length, but inversely proportional to area. Right. This is what they are saying there. And then when considering what we discussed on the previous slides, we now have 2 things like that. So when you look at this wire, thin wire, there's not much space, high resistance. But look at the thick wire, the space is in between, right? More space, hence there will be low resistance. The electrons are free to break through and go nicely. But here, it's like it's a straight line. There's not much space to vibrate about, to move about, right? That's what they are trying to explain here. When they're saying thin wire, not much space, high resistance. Thick wire, there's some space in between, more space, hence low resistance. Also note that when resistance is increased in a circuit, for example, by adding more electrical components, the current decreases as a result. This is what we're talking about in the previous slide, this one. When we're using like 2 bulbs there, that's high resistance, low current, 1 bulb, low resistance, high current, right? Now, is what is called Ohm's law. Ohm's law, George Ohm. It's related to EMF to current in his simple law. Ohm's law states the ratio of voltage to current is constant. Right. The ratio of voltage to current is constant. That is voltage towards I is constant. That's why it's going to lead to V is equal to IR, but let's not rush. So the ratio of voltage to current is constant, provided other physical factors such as temperature remain unchanged. So the meaning of this is that the amount of current in a circuit is directly proportional to the voltage across the circuit and is inversely proportional to the resistance of the circuit. Right, let's put it mathematical. The amount of current, that's I, in a circuit is directly proportional to voltage, that would be directly proportional to V across the circuit, and is inversely proportional to the resistance of the circuit, that's inversely proportional over R. Hence, that leads to V is equal to IR, what we're talking about. Voltage is equal to current times resistance. Hence, by applying Ohm's law, we can find out about resistance, which is an important physical property associated with all circuits. So using this Ohm's law, we can now find out about the resistance, which is an important property, right? Let's go and talk about that. So as we said, voltage is equal to current by resistance, of which we've already talked about this. I don't know what this person who sent dots to everyone is trying to say, but voltage is equal to current by resistance, V by IR. We talked about this last time. V volts, current M's represented by amperes E. Then resistance, its SI unit is ohms, right, which is represented by this sign. That means ohms. The equation can be rearranged to find the resistance. That will be R is equal to V over I. That's resistance is voltage divided by current, right? Now, Ohm's law, a conductor has a resistance of 1 ohm. If a potential difference PD of 1 volt across its ends causes a current of 1 ampere to flow through it, R is equal to V over IR. Another one, 3M flows through a 240 lamp. What is the resistance of the lamp? Right. So we're given I current, right, is equal to 3 amps. And then I told that the potential difference of 240 volts is flowing through the lamp. Then they're asking you, what is the resistance of the lamp? As suggested, the resistance is equal to voltage over current. Hence, R will be 240 volts over 3 amps. 3 day 1, 3 to 24, 8, that's 80. Hence,
80
ohms. Volts per ampere. That's R is equal to 80 ohms. You are right on that one. Now, let's go to the next one again. Someone was talking there. There's a hand raised to it. 80 ohms, yes. Now, the 4 constituents of a basic electrical system. Right, listen to this one so that you understand what a circuit is. Right, what an electrical system is. The 4 constituents of a basic electrical system. Right. Let's go. 1, I want to annotate. 1, we have the source. The function of the source is to provide the energy for the electric system. A source may usually be thought of as a battery or generator, right? So a source is either the AC mains, a battery, a solar cell, or whatsoever. There must be a source. For everything, there is a source. Even a human being needs food, right? There must be a source of energy. Then there must be a load. What is it that you're trying to turn on or to use or to function? An electric kettle, a stove, a light bulb, a car, whatsoever, right? The load, the function of the load is to absorb the electrical energy supplied by the source. So for a human being, the source is food, like the load is you. You absorb, you chow that food so that you can do other things, exactly like an electrical system. There's a source, the battery, and then there's the light bulb, which chows the battery power to turn on, to light for us, right? So the load, the function of the load is to absorb the electric energy supplied by the source. Most domestic electric equipment constitutes of loads. Common examples include lamps, heaters, like for example, today the weather is unfriendly, kettles, stoves, etc. Now, there's number 3, the transmission system. This conducts energy from the source to the load. Typically, the transmission system consists of an insulated wire, like this. Number 3, the transmission system. For example, for a human being, the transmission system is the one, the blood, isn't it? The engine, the stomach absorbs the food, and then the blood system absorbs that food from the stomach, and then it rounds up through the entire human body. So on an electrical system now, you have a source, as we say, the battery, and then you have a load, which we said, for example, a lamp. But in order for the lamp to chow that battery, it must be connected. So each connection is wires. For human beings, it's arteries and veins. But for that lamp, it's a wire, an electrical wire, which conducts that energy from the battery to the lamp or the stove, which is usually insulated by plastic, as we say, right? And then there is number 4, the control apparatus. As the name suggests, its function is to control. The most simple control is a switch, which permits the energy to flow or else interrupts the what? Flow. So everyone knows a switch. You flip it on, it goes on. For a car, it's an ignition key. Flip it on, it turns on, right? So that's the control there. Right, simple circuit, draw a diagram. For example, I can put this one from my head right now, where I can say here is a battery, positive side, negative side, go on, put a resistor. This is complicated, but not that complicated. Go on, put a light bulb here, right? Usually represented by an X, go back. And that's a simple circuit. If a battery, as we said, which is the source, we have a load, which is these two, right? With wires, which is the transmission system. In what done? When you go back to your 4 points, you can start. The source, the battery we have, the load, the resistor, and the light bulb we have. And then you go on, the transmission system is the wires we have. The control apparatus is the one that we don't have. So now we can go on and add the what? A switch here. Right. You can go on and add the switch to control that. And there, see if I have a switch. There is a switch. Right. So this switch, when it's flipped on or off, flip on, complete the electric circuit, you're controlling the light bulb turns on, flip off, it's out. So this is your control, which is the switch. So you see source, battery, load, the transmission system, which are the wires, control system, which is the switch there. So that's an example of a simple circuit of the transmission electrical system. Now, simple circuit. They even gave us another simple circuit now. On this one, take a look. We have our source, battery, or source. We say it's called the source. We have our control, which is the switch. We have our wires, which is the transmission system. Transmission. These are wires, right? And then we have our load there. Let's say, which is, for example, let's say a bulb, right? So our four things are already there. 1, 2, 3, 4. Then now we have an extra thing. We have a voltmeter. As we said, it's plugged across to measure volts that our bulb is showing in the circuit. So that's an example of a simple circuit. Now, the system in systems with increased loads. Now, this is a system with more than one load. So electrical technology is very complex. E.g., of a simple circuit seldom exists except in batteries or torches. In this regard, let's look at systems with an increased number of what? Of loads. To handle two or more loads, we need to be adept at recognizing series connected and parallel connected circuits. So what they are saying with the word adept, you know, English is a problem. So they are saying to handle two or more loads, we need to be adept at recognizing series connected or parallel connected. That means we need to be well vexed. We need to be smart about it. At which one? At recognizing the series connected and the parallel connected loads. Now, series and parallel connected loads. Loads are series connected when the same current flows through each of them. So what they are trying to say, they're saying when load number 1 is here, let's call it L1, and then we connect L2 there, and then we connect L3 there. So these things are connected in series. Series meaning it gets in, comes out, and then gets in, comes out, gets in, comes out. It's a line. So this is a series connection. So in a series connection, same current flows. So the current I1, which is in here, is the same here. We're going to have I1 still here on L3. I1 is the same current. So in a series or a line connection, current doesn't
Vuyiswa Ntuli, you are now a host. Say something.
Guys, don't leave. Cecily got a connection problem.
Okay.
Bani lo Simbuka la? Bani lo Simbuka la?
Right, I'm back. I think I had a connection problem there. So my network went down for a second. Let's continue. Right, let's see where we were. Mhm. Right. We're now talking about these things, about parallel laws. So yeah, we're here. I was saying to you that we said the series is like this, right? Like that, like that. We call this L1, L2, L3. We said for this one, current is the same for everybody here. Doesn't change. On a series connection with the same current, but the potential difference across this guy here, and the potential difference across this guy here, and the potential difference across that guy is different. So voltage is different. Right. The voltage depends according to the resistance of this guy and the resistance of this guy. Remember, we said V is equal to IR, right? So for the first one, with V1 is equal to same I, which is I1 by R. And then the other guy, which is V2, this one, we're gonna have the same current I, but R2 here. Then the third guy there, we're gonna have V3, which is I1 still, but R3. So you see, the voltage will be different because it depends on the resistance of these loads. But current on a series connection is always the same. All right. So now let's talk about the parallel connection. By parallel connection, things are no longer in line. You see, series is in, out, onto the next. But parallel, they are sharing. For example, this is a node to junction. Now we have L1, load 1, and then now we have load 2, and then we go on, meet goes out. So you see that instead of in out on one of the loads and then into the other, but they share. Here it's split into two, goes into L1, goes into L2, then they meet again on the front. This is what is called a parallel connection. Right. So for parallel connection now, the voltage now is the same, but current is different now. So here they share current. Current is shared, share current. Right? But voltage V is the same. right? Remember, we said V is equal to IR, right? But now V is constant. Current is shared according to the resistance there. So in other words, I there is V over R, right? So you see, current will be different because of resistance. Now voltage is the same, but the resistance of L1 and L2 might be different. So for block 1, we have I1 will be equal to V over R1. And then for block load 2, we're going to have I2 is equal to same V, but over resistance 2. So the resistance here is determining the current. The voltage is the same, but current is different. So current is shared here. So remember that series connection, current is the same. The rest is different. And then parallel connection, voltage is the same, but the rest is one is different. Now, properties of circuits, series connections, right? We say the components that are connected one after the other on the same loop of the circuit, they are connected in series. We say the current that flows through each component connected in series is the same. The circuit diagram shows a circuit with 2 lamps connected in series. If one lamp breaks, the other lamp will not work. Why? So let's start from the basics. Here is our source, as we say. Here is our control, which is a switch, as we say. Here is our transmission system, the wires, as we say. Here is our load, as we say. Right? That's a complete circuit. From there, we said there's a series connection. These two are connected in series. That's lamp 1, that's lamp 2. Right? But now, they are saying that if one lamp breaks, the other lamp will not light. Why? Because they are interconnected to each other, one after the other. If this one breaks, that means there is an open circuit there. That means now we have something like this. Open, lapper, and then we have a bulb. And then we continue, we have our battery there, and then we have our connection. So if the here is open, we do not have a complete circuit, right? So if this one is broken, that's an open circuit. Then which means it's broken, electricity doesn't flow through. Hence, this one will also not light if this one is broken. Vice versa, if this one is broken, this one will not light, right? That's the problem with what? The series connection. If one breaks, the other won't work. But it's different with the what? With the parallel connection, right? So now, let's go to the next. Let's clear that. So now, calculate the equivalent resistance of a circuit connected in series with 3 resistors of 4 ohms each. What they are trying to say here is this, is that consider a circuit where their resistance is like this, all 3 of them, right? Connected in series, load, like that, switch, like that. Right, they are saying these R1, these R2, these R3, right? They're saying R1 is equal to what? 4 ohms. 4 ohms. This one is also equal to 4 ohms. This one is also equal to 4 ohms. Right. And then they are saying calculate the equivalent resistor of the circuit connected in series with 3 resistors of 4 ohms. Right. So here, the law that we talked about, we say V is equal to IR. And then remember, we say on a series connection, what happens? The current doesn't change. So in other words, we're going to have V1 is equal to the same I, but R1 plus, for the other one, we have V2 is equal to I by R2. For the other one, we have V3 is equal to I by R3, right? So the total voltage in this cell is going to be V1 plus V2 plus V3, right? Just do it this way so that things are clear. Do it this way. share whiteboard. Right. Share whiteboard. And then pen. So let's take it like this. We have one after the other, one after the other, one after the other. We say it. Right. We have R1, R2, R3, 4 ohms, 4 ohms, 4 ohms. Right. So here we have V1 is equal to I R1. V2 is equal to I R2. V3 is equal to I R3. Current is the same. Remember, we said current in a series connection doesn't change. So what is the total voltage there? The total voltage is supposed to be V1 plus V2 plus V3, right? Of which that will be same as I1 R1 plus I R2 plus I R3, right? And then since this I is what is common, we have I that will be bracket R1 plus R2 plus R3. We factorize I. So you see how the resistance is done here. It's simple just adding these resistance. So total resistance, right, in a series connection is simple. You just add all. So the total resistance will be R1 plus R2 plus R3. That will be 4 plus 4 plus 4, which is equal to 12 ohms. Right? Simple and straightforward. So that's what they were trying to tell us there on that one. Let's go very fast to where we were. Now we've covered a lot. Yeah, we're flying. So this is what they were saying, that the equivalent resistance in a series connection, you simply just what, as you can see, you simply just add the resistors. But now I showed you how and where the adding came from, how it was derived. So you simply just add those resistors together. All right. So the comrades, so far so good. Are you okay, comrades? The comrades are quiet. When the comrades are quiet, I assume the comrades are doing well. So are the comrades doing well?
Yes, everything is clear.
Ah, that's wonderful. If the comrades are doing well, that's wonderful. So now let's continue. Properties of circuits, series connection. So series circuits are useful if you want a warning that one of the components in the circuit is failed. So this is one way of tracking. If your things are connected in series, if it doesn't work, you know that one of them is dead, broken, etc. Right. For example, you know this one, the plugs at home you've seen or you heard about a thing called a fuse. For example, on a circuit breaker, a fuse must be connected in series in order for it to work. If Christmas tree lights all go out when one bulb breaks, they are connected in series. That's another example. So the sum of all the potential differences across the components in a series circuit is equal to the total potential difference across the power supply. Now, in a series circuit, resistance is not the same. In a series circuit, only current is the same, right? only current is the same. So the rest are different. So now I want to explain this statement. There is a law which talks about this thing. This statement is called Kirchhoff's voltage law. Kirchhoff's voltage law, abbreviated KVL. Right. So KVL says, like they are saying, the sum of all the potential differences across the components in a series circuit is equal to the total potential difference across the power supply. So what they are saying in simpler words, they are saying the power supply, your source, is equal to all the voltages that are charged in that circuit. All voltages charged in there. Right. So in other words, that circuit that we drew, where we had V1 plus V2 plus V3, that must be equal to the source of battery power, right? Where here we had now IR1 plus IR2 plus IR3. So you see, Pilangoshi, you were asking, only current is the same in a series circuit, but resistance is different, right? But the total voltages, since we said V is equal to IR, of all these three loads, right, must be equal to the source that supplies them. Right, that's Kirchhoff's voltage law, KVL. It says the sum of all potential differences across the components in a series circuit is equal to the total potential difference across the power supply. Right. I hope you are answered there in that one. Now, let's talk about properties of circuits, parallel connections. Now, parallel connections, as I said they share. It's like this, and then you have a certain load there, and then you have a certain load there, then they meet again here, right? Hold on a second. Right. So the parallel connection, right, that we're now on about, we said they share and then go through, and then meet again like that. So components that are connected on separate loops are connected in parallel. For example, look at these two. They are sharing again, right? Comes here, shares, goes there, and then goes there, they meet again. Just like that connection there. So for parallel components that are connected on a separate loops are connected in parallel. The current is shared between each component. So here we say that voltage doesn't change. Voltage is the same. What's different is current, right? There is I1, there is I2, but V is the same across, right? The total amount of current flowing into the junction or split is equal to the total current flowing out. The current is described as being conserved. So here there is something also called Kirchhoff's current law. Kirchhoff's current law, abbreviated KCL. So what Kirchhoff's law says, it says the amount of current flowing in, like here, there's a current flowing into this junction. Let's call that I1. the total amount of current flowing into a junction or split is equal to the total current flowing out. So there will be current flowing that way, current flowing that way, call that I2, I3. So what it says, I1, which is coming inside the junction, must be equal to what goes out of the junction, I2 and I3. So whatever goes in must come out. That's the rule about what KCL. So whatever goes in must come out. It went in, it must come out, right? So if, for example, we have a junction like this, with a current in, and then we have a current in, and then we have a current out. Let's say I1, I2, I3. This plus that must be equal to that. If, however, we have a different, we have two going out like this, they are going out in a junction, one going in. This plus that must be equal to that, right? That's Kirchhoff's current law. The circuit diagram shows a circuit with two lamps connected in parallel. If one lamp breaks, the other one will work. So check this one. Since they are sharing, remember the series connection, they were like this. So which means if this one breaks, it will now be like this, an open circuit. Therefore, electricity won't reach this one. But here on a parallel connection, if this one breaks, we will have something like this, open circuit, like this, right? But still have another connection going in here. You see, they are sharing, still continuing this side. So if this one breaks, this one will work. If this one breaks, this one will work, right? So that's the difference there. Yes, current divides on a what? On a parallel connection, but it doesn't divide equally. It only divides equally if, let's say, this is 4 ohms. So someone is asking that does current divide on a parallel connection? Yes, it does divide, but the division is rules. If this is 4 ohms, they are all the same, it will divide what? Equally, right? But if, however, this, let's say, is 6 ohms, this one is 4 ohms, obviously it won't divide equally. This one with 6 ohms, right, will take a certain amount of current, and this one will take a certain amount of current. However, the rule about that is that current tends to flow where there is less resistance. So which means the one with less resistance will get more current. The one with high resistance will get less current. That's how the sharing goes. But we'll get on to the calculations of how they share this current. Now, so calculate the equivalent resistance of a circuit connected in parallel with 3 resistors of 4 ohms each. So for parallel loads, the total resistance RT, the total resistance, this is how it's found. You say 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Right. Once you calculated the end, then you invert. That's when you're going to get your total resistance. So for example, here, they say each of 4 ohms. So you say 1 over RT would be 1 over 4, 1 over 4, 1 over 4. Remember, 1 over RT would be equal to 1 over R1 plus 1 over R2 plus 1 over R3, which is exactly what they did there. 1 over RT is 1 over 4 plus 1 over 4 plus 1 over 4. And then it's still 1 over RT here is equal to 1 plus 1 plus 1 over 4. Still 1 over RT there is equal to 3 over 4. But now, to get RT, you invert. Invert means bring it back. So it will be RT over 1 is equal to 4 over 3, which means total resistance is 1.33, which is 4 over 3, right? So do not forget, for parallel connections, we just go there and say 1 over R total is 1 over R1 plus 1 over R2 plus 1 over R3, all of them in there. In the end, invert this and invert on the other side. You get your final answer. Right. Now, let's go on to the next. properties of circuits. Now we're talking about the properties of what? Parallel circuits. Those are the ones that we are concentrating on. The lights in most houses are connected in parallel. Have you realized that if one bulb at your home is not working, the other ones are working in the house, but they are all powered from the main switch? That's a parallel connection, right? Because imagine if the whole house depended on a series connection, which means every time one bulb blows, the other people in other rooms, they can't see. That would be a poor decision, right? On the electrical engineer or whoever wires the house. So for a parallel circuit, the current from the electrical supply is greater than the current in each branch. What they are trying to say there is that the source that gives you the big I before sharing, its current is bigger than the currents when it is now shared there. The source always has a bigger current. So the sum of all the currents in every branch is equal to the current from the electrical supply. As I said, whatever goes in must come out. Whatever comes out must be going in. So that's what they are saying there, Kirchhoff's current law. And then now we went on to what is called power in electricity. What is power in electricity? Right. Power is the rate at which energy is delivered to a load. Right. What is it? Take note of these things. The rate at which energy is delivered to the load, or the rate of energy transfer, or the rate of doing work in a circuit. It's called an electric power, right? But the best delivery, the best one is this one here. The rate at which energy is delivered to a load. So electric power can be measured by the product of current and voltage. So what they mean would be that power is equal to what? IV. Current times voltage. So you have to take note of these. You have to take note of these formulas. If you do not practice, if you do not follow the notes, you will never get them. But if you practice and follow the notes, then you will get them. So that's what is happening here. Electrical power can be measured by the product of current and voltage. Mathematically, that's how it's written. P is equal to IV. Right. So electric power is measured in watts. That's the SI unit, watts, abbreviated W. Right. That's 1 watt of power is the result of 1 ampere of current being driven by 1 volt of force through a circuit. Here this 1 watt of power is the result of 1 ampere of current driven by 1 volt of force through a circuit. Right. So I think we have finally come to the end of this section of electricity and don't know. So now, I don't know, should I continue hammering you or should we call it a day? And tomorrow we start on something else. You tell me. I can continue hammering if the heads are still fresh. Someone sent, call it a day. Joshua is saying, call it a day. What is the rest of the class saying?
Because some of us have to be on campus for a practical that's starting at 1 o'clock. So
Someone
Yes.
says I should continue hammering. So I should continue hammering.
No, say we can call it a day because others are going to attend the practical at 1 o'clock, so they have to be there on time.
Oh, the majority says let's call it a day. All right, I don't want to hammer you too much.
Yes, let's call it a day.
All right, I'll call it a day. Have a good day, guys.
Thank you so much.
Sir.
Have a good day.
Yeah.
So sorry. You said that you're gonna upload the videos. Well, obviously in your time.
Yeah.
Do you mind by any chance separating when you're uploading the videos, separate them into the categories, not just upload them all at once? Like, like in random orders.
No, I'm not gonna put them in random orders. I'm gonna put them according to their order of following each other.
Okay, perfect. Thank you.
Depend on what day is gonna be written, labeled that day.
Okay, perfect. Perfect. Thank you, sir.
Yeah. Any other questions?
Sorry, sir, there are two quizzes that are open.
Yes. 2 quiz, or you mean a quiz and a practical?
Oh, yes.
Yes.
When should we attempt them?
Yeah, the time is written on Moodle. We discussed that last week. Check the course outline about what we said. We said the tutorial what is going to be given on what and is due on that particular week. And the other one, I opened it is due on whatever week. So open learn, you will see the timelines.
Okay,
I
thank you.
discussed the practical with the class, what they should do and etc. Not the practical, the tutorial of what's applied there. So just follow us there.
Thank you, sir.
Any other questions? You see, it's very important to attend class, because if you attend, you get to hear what I'm saying. If you don't, you're in trouble. So, any other questions? All right, I'll stay on for about 3 to 5 minutes. Maybe someone is shy. They want to ask Kebona secretly, Nicodemously. I'll be here.